Okay, so remember at the end of class last time, we defined the degree of a continuous map between positive dimensional spheres. So here's that definition again. So if we're given a continuous map between positive dimensional spheres, consider the induced homomorphism between the homology groups of degree, which is the dimension of the sphere. We've computed that the nth homology group of the n sphere is canonically isomorphic to, so I'll just say equal to the integer z as a group. So the continuous homomorphism determines a homomorphism between the integers, so from the group of integers to the group of integers. And I just put a note, this homomorphism is determined by its value on the generator, preferred generator of the integers, which is the number 1. And so in that way, we get an integer assigned to every continuous map between these positive dimensional spheres. And that's the definition of the degree. As a quick example is the degree of omega n, the winding by n map from the circle to the circle. In that case, the degree is just equal to n. One way to see this is that we already saw that the map on fundamental groups, I'm ignoring base points, we've already seen that that map on fundamental groups carries 1 to n. And first homology is the abelianization of fundamental group. But these are already abelian groups. So these fundamental groups are equal to the first homology of the circle. I wanted to give just a remark. This way of obtaining a number, a numerical invariant of a continuous map is rather powerful, as we will see in some applications right away. But so I wanted to remark on another way of obtaining a numerical invariant from topological stuff. And that's a linking number. So what is a link? Well, a link is an embedding of the disjoint union of two circles into R3. And by embedding here, I mean like a topological embedding. It's a continuous map that is a homeomorphism onto its image. That's L, that's the map. So that continuous map determines another continuous map from the product of two circles. Of those two circles, I put an index plus and minus on them just to distinguish them. So this link determines a map from the product of two circles to the two-sphere, given by this expression. The value on a pair of elements, one in each circle, PQ, is the vector, the unit vector in R3 that starts at Q, at L of Q, and goes to L of P. So that's this vector in R3, and then we normalize them to make it a unit vector, thereby giving a map, an element of S2. So that defines a map from the torus to the two-sphere. Every link determines a map from a torus to a two-sphere. And we can apply the same idea as the definition of degree to obtain a numerical invariant of this link. Namely, you can apply second homology groups, the torus and the two-sphere, and we computed in class that the second homology of the torus is the integers, and the second homology of two-sphere is the integers. So there is then a homomorphism from the integers to the integers, and again, the value that such a homomorphism is determined by its value on 1. And the value on 1 is what we call the linking number. And there will be an exercise which is to compute the linking number of a couple examples of links. And to that point, these are nice definitions: degree, this numerical invariant of a continuous map between spheres, and linking number. But how on earth do we ever hope to compute those things? So that's what we're about to develop next.